So we've made this big picture point that if you have the stratigraphy and the information that you've used for Smithville, for instance, you don't get that for nothing, and so you have to physically acquire that. And so the methods of acquiring that are through direct site investigation, drilling and sampling, drilling to be able to figure out what the stratigraphy looks like if you use a borehole camera, but also sampling in that profile to be able to look at stratigraphy. Not just knowing whether it's a sand or a silt or a clay or a granite, but also knowing something about the parameters of interest, which would be things like permeabilities, which you might measure in situ or by taking stuff back to the lab, and maybe inferring capillary characteristics from the techniques that you've used in your assignments in this class as well. The fact that the cost of this direct site investigation is expensive, and so once you've drilled a hole, you might want to do something with it, like put in piezometers or use straddle packers to measure permeabilities and get profiles of those. And also the fact that other newer methods of doing this are by using continuous profiling, by putting a probe into the ground and measuring the resistance to that being forced into the ground, and also the pore pressures that are generated at the tip, and then using that to create basically a profile of permeability with depth. And so that's kind of some of the basic information that you would get from logging along linear features, a borehole or a cone probe push path. If you don't put instrumentation in, you might want to seal it with something because you don't want to leave aquifers that are interconnected. In fact, when people talk about CO2 sequestration, apart from this class, big picture questions for them are that if you go into pre-existing petroleum reservoirs that have been depleted and use those as the place where you'll store the CO2 so it doesn't go into the atmosphere, so burn it, take it out of the flue stream and push it underground. One of the egress methods for that, perhaps the largest one, is fugitive emissions along pre-existing unplugged boreholes. Because 50, 60, 80 years ago, people used to drill holes looking for oil, and if it wasn't successful, you just walk away. You don't plug it to stop it from communicating to the surface. And so if you don't put instrumentation in these, then oftentimes you'll backfill the hole with grout just so there's no communication. And I think even with the geoprobe methods, when you withdraw those, often they'll be backfilled along the path of this probe just by squeezing out grout so that you don't end up with, again, this small hole that will collapse that will allow aquifers to communicate. So drilling is one way to do it. It gives you only a linear profile in a very restricted area. I'm not sure what density. You saw the density for Smithville. Maybe there was a drill hole every 20 feet away from each other. And so in that particular site, it may be 20 meters, so it's 60 feet deep. So it's a trivial depth, so you can afford to put these things down wherever you need. If you get to be working on a larger site, then maybe you can't afford that density. And so the other way to fill in between things is by using geophysics. And geophysics is best used where you have an initial borehole as confirmation or some kind of profile of confirmation. You run the geophysics, it looks at some particular proxy, and then you benchmark it against that hole and you extend it to the other locations to be able to infer what's there. We talked about a few of them. They all work by this idea that they look at a proxy. So geomagnetic methods look for changes in the magnetic field of the Earth in a very local area. Can only pick out targets which are different from the surroundings, and they have to be different magnetically. And so it'll pick up not all metals, but only ferrous metals, because they have magnetic susceptibility. And we talked about proton magnetometers walking across sites, and also campaign style, where you physically take an instrument and move it from location to location and get a more direct reading. Geoelectric methods we started talking about last time. We said that they use, we only talked about DC methods so far. We haven't talked about alternating current or electromagnetic methods. But the basic idea was that we're trying to measure the electrical conductivity or electrical resistivity, the reciprocal of conductivity of the subsurface. And if we know that garbage versus sand versus granite have different resistivities, we can then distinguish between those different media and be able to map between them. We said that they worked in different modes. You could use them in kind of drilling mode by expanding the array and looking progressively deeper. So you have a profile of resistivity that you could check, for instance, against a borehole. And then if you do it at some other location, then you're basically doing another borehole but not drilling a hole to be able to see what's going on. Or you could use them in kind of a profiling mode to be able to take the same array and just transpose it down the pipeline alignment or the road alignment to be able to see if there are any anomalous conditions that you see which would represent maybe something that you'd want to know is there. Could be the edge of a landfill, could be some drums, of course. Metal will conduct electricity as well. All metals will in this particular case. Or in some cases, if you had salts in a plume, you might be able to pick that up as well. So you can map plumes with it. And so we talked about using that and using it also in terms of tomography to be able to say, to monitor the progress of cleaning up a site. So if, for instance, the saturations of TCE change the average resistivity of the site in place, then as you remove that stuff, the resistivity will change, and you could actually map that in some way. Okay. So the other ways of doing it are using AC methods and electromagnetics. And those are actually a bit exotic, I think, for the environmental area. They're used in things like looking for ores, for prospecting. And the idea is that if you had some kind of array of probes and you turn on the current so that you're flowing electricity into the ground and then you turn it off, then instead of just measuring the steady state voltages, what you can do is you can put current into the ground over some period of time. This is time on this axis. Then turn it off. And what happens is you turn it on, you generate a voltage. You reach a steady state voltage, which is basically the voltage that you'd measure between these injector electrodes and these measuring electrodes, which in the steady state would be a single value. It would change as you change the separation, but it would be a single value. But as soon as you turn off this flow between A and B, all of a sudden what's going to happen is the voltage that you measure between those will decay and drop down to background. If you put the negative current on, then you'll build up the opposite voltage potential, and as you turn it off, it'll decay again. So the idea is that by seeing something about the rate at which it decays, you can say something about the target. It's not used in environmental methods very much, but that's just the methods. Too exotic. But by far and wide, the standard DC method is the way to do it. So of these three methods, I guess it was right. No, okay. So of these three methods, DC is used largely, widely used. It's very simple, very inexpensive. Relatively unskilled people can do it, but typically an environmental company wouldn't do it themselves. They'd hire a company like Western Geophysical who'd come out and do the survey for them. Or some companies might rent the equipment to be able to do it. The equipment for DC electric is so inexpensive that it wouldn't be very difficult to own it. AC is very exotic, and electromagnetic methods some are used. Some small-scale ones are used. They divide themselves between two general types. Large-scale electromagnetic methods, time-domain electromagnetics, and ground-penetrating radar. The large-scale electromagnetic methods use large arrays. Some of them use electromagnetic signals that are naturally occurring. Submarines communicate by using electromagnetics. And they use very low frequencies because those don't get attenuated as you travel. So if you have very high frequency seismic waves or electromagnetic waves. Those get damped out of the atmosphere very shortly. The longer period waves have higher amplitudes and endure more. And the idea is that you have some kind of transmitting coil that transmits an electromagnetic wave. You have a target which modifies it in some way, and you measure how that wave is modified by the target, and you interpret it in some way to be able to figure out what that target is. And typically these are used for targets which are not hazardous wastes, but are things like ore deposits, which might be kilometers deep, kilometers in size, and therefore the scale of these surveys are correspondingly pretty large. But the one method, I guess, which is used quite broadly in the environmental areas is Gpr. And so it's no different than the radar that's used to pick up aircraft, different frequencies. It's pushed into the ground. So what you'll have typically is a transmitter that has a continuous pulse of waves that are pushed into the ground. You have a receiver which is separate from that. They may physically be separate objects, or they may be in the same object. And the idea is the transmitter transmits a pulse. It goes down to an interface. Once it hits that interface, if the interface has a dielectric contrast, so in other words, the dielectric constant of the material 1 is different from 2, and 2 is different from 3, it will reflect off this, and it will come back to the recorder. And so there are two essential features. One is that the proxy here now is not resistivity or changing the Earth's magnetic field. It's actually dielectric potential for the material that you're measuring it. So if you want to measure stratigraphy, then the different rocks have to have different dielectrical potentials, which they do. And if you want to use it to pick up a plume, then the plume has to infer a different dielectric constant to the rocks with the contaminated water in it versus non, because that allows you to get a reflection. But the actual component is that it measures the time of flight for the transmitted wave to go down to the interface and then bounce back up to the surface. So it measures basically the time it takes for this to be emitted, to travel down to here, and to be returned here. And it measures it just like a reflected seismic wave. But the wave is not seismic, it's not an acoustic wave, it's a radar wave. Okay, so what's it's written here? So as you can imagine, you can pick up planes beyond, it has to be line of sight, but they can be not visible to the naked eye if it's powerful enough. So you only have a certain amount of energy in it. And so rocks typically attenuate it much more quickly than in the air. And so the depth penetration you get is not as large as it would be in picking up aircraft. So maybe you can get down 10 or 20 or 30 meters in terms of this depth. And so beyond that you can't go. What you can do is you can change the frequency at which you have this transmission. And so lower frequencies are attenuated less than higher frequencies. And so lower frequencies allow you to get deeper, but higher frequencies give you better resolution of your target. As I say, it measures dielectric constant, and the depths of penetration are controlled by the different materials. And so air is huge, kilometers, but if you're talking about geological materials, then things like water allow it to go quite a long way, but typical rocks allow it to go less, and some materials completely mask it. What else? Yeah, so that's it. So, so the two features that are important are the dielectric constant and the velocities. And so dielectric constant allows you to get a reflection from some contrast between two beds maybe that have different magnitudes, or between a plume which has outside it uncontaminated stuff with a different dielectric constant from stuff inside it. And so that allows you to get a reflection. But the reflection, the travel through the material is actually conditioned by the velocity, which is also a very slight function of dielectric constant. So as you change the dielectric constant for these different materials, the velocity in meters per millisecond is changed. Not very much. So the fastest, I think, is probably for air, which makes sense. And the slowest is a factor of maybe, well, it's 5 times less. Seawater is, I guess, 30 times less. So it's actually not so slight. But the velocity is changed to some small amount by it. It's actually the transmission velocity. And I presume electromagnetic radiation is just the same as light. So this should be the speed of light, or close to it, I think, in air. Or in a vacuum, it would be anyway. So you can check out whether that's the case or not. And so this is a typical profile. So this is actually exactly the same. Yeah, it's exactly the same time. Look at the date on this thing. So we're talking about HAZWOPER and getting certified in something because they might want to send you somewhere quickly. This was done on that first deployment. And so what it was is it was in Norman Wells. It wasn't for looking for contaminants, but the idea was to put some artificial islands in the middle of the Mackenzie River as drilling platforms. And so what this was a winter campaign to drill holes in the middle of the seabed, the riverbed. And winter is used because in wintertime the river freezes and you can drill from the surface. And so this was one drill hole which was present. The key for this, you can see down here, is a meter of ice at the top, water down to the bottom of the riverbed. I don't see a scale off to the side. It's missing its scale. It's been truncated. Oh, it is there. This is 0, 0. This is, it's not 50 meters. I don't know what the number, yeah, it doesn't matter what the numbers are. Certainly it's not 100 meters. It's not 1 meter. I guess it could be 10 meters. I guess maybe it's 5.0. So something of that order. So this is water, and then beneath the water there's sand, and beneath the water there's clay. And so you have that from your borehole. In this particular case, these were drilled with a diamond drill core barrel, and the sand was not sampled. It was just came up and disturbed, but the clay was hard enough that could actually be drilled into, and plugs of it were retrieved. And so the idea is now that you have this borehole, you absolutely know what is physically here. So now across the top of this surface, you drive a Gpr unit. And you use this Gpr unit to get this profile. So this other kind of messy profile is what a Gpr profile looks like. So the idea is that you have sitting here a transmitter, you have a receiver, and what it does is it measures the time of flight that it takes for it to go down here and come back up. It takes this time of flight and it plots it as a trace. So this is some amount of nanoseconds. So these, oh yeah, okay, so that's what this is. So these amounts are not depths of this hole. These are 50 nanoseconds, 100 nanoseconds, 150 nanoseconds, 200 nanoseconds. And so the time of flight at this point for this reflection to come back is something like 25 nanoseconds. For this one here, it's something like 80 nanoseconds. And so this is one profile you get from the instrument physically being in this position here. You drag the instrument continuously along the surface of the ice, and it just does that incrementally all the way across. So you have this profile of these travel times. You take the travel times, you know something about the magnitude of the velocities, if you know what the material is. Water, for instance. This is fresh water, I guess, in this particular case. If you know the velocity that you expect in fresh water, then you can take a magnitude which is 25 nanoseconds to go both ways, and you can figure out exactly how deep this is because you know what the velocity of transit is. That's how it works. And so you know this one is 80 nanoseconds for two-way travel. If you think it's going through a combination of ice, then water, then I guess it would be only those two things, then you can figure out what the magnitudes would be. And so the bottom line is that since it's really only a relatively weak weakly conditioned, this velocity only changes slightly as you change the materials, you can think of this profile as basically a profile of different interfaces. So this is the bottom of the ice interface here as it goes along. Pretty constant, you'd expect, as it goes across here. This is, maybe this one is the profile for the riverbed as it goes across here. And the one that represents the interface between the sand and the clay that overlies it, you get this interface going here, is this track that it goes across here. Yeah, so this is, if you can read this. And so you pick up this as it goes across, and you need the eye of the faith to be able to pick this up. But that's basically the idea. So it's really very straightforward. So it's not clear whether you would do that interpretation. Maybe if you're in a small company you would, or maybe you'd, as I say, you'd get another larger geophysical unit to mobilize the equipment on site and just do the interpretation. So GPR is used a fair amount, one, to pick out stratigraphy. It has also been used, it was used, for instance, at Borden. If you remember some of these examples we looked at, we had the plumes disappearing downrange for a conservative tracer, where the plume size grew with time as it kind of spread out. And if you looked at the non-conservative components, they traveled less far and less fast as the other components. Well, for one of the examples, GPR was used to try and look for those plumes as they disappeared downrange. And so these components tend to be not polar, and therefore they're not really picked up very well by GPR, but there is some kind of signal attached to it. So GPR is pretty broadly used. So if you watch things like crime scene shows where they're looking for dead bodies underground and use GPR, it's exactly the same application. So the proxies that we use are the Earth's magnetic field, DC, AC, and electromagnetic waves. And so GPR is by far the most broadly used one in this category. These boxes with DC electrodes, Venner and Schlumberger arrays are the most commonly used ones for DC methods. Seismic methods are lightly used, I guess. I say lightly primarily because the proxy that they pick up is the acoustic velocity, or the P wave velocity, and the S wave velocity of the soils. And that doesn't change very much with how much contaminant you have in it. And it doesn't change all that much even with how much water you have in it. And so the signals that you get, the proxy, the acoustic waves aren't very sensitive to things that you might be interested in. But it is used, and it is used to be able to pick up mainly stratigraphy. The principles are pretty straightforward. It's just like GPR, except now the two necessary components are that between different layers, the thing that causes reflection is called the acoustic impedance. I think it's N's impedance. And the acoustic impedance is just the product of the density of the material and its acoustic velocity. Acoustic velocity in air is 500 miles an hour. In rocks it's larger because they're more dense. But so long as the product of the density of each of these layers and their velocities are different from each other, you will get a reflection from them. And or the waves will travel differently in them. And so that gives you the signal, and then the quantity that you use to be able to interpret it, just like the electromagnetic radiation velocity in GPR, is the acoustic velocity. And so it's the product of density and velocity that give you the reflection or refraction, and it's the magnitude of the velocity that you use to actually reduce the data. And the basic idea, actually I don't know if, actually it screwed us up last time, so I don't know whether I should do that or not. Well, let's give it a give it a try. Let's look at something else. So I was looking at these technical photos. Did I make this large? Let's see if I can find them. I'd forgotten about these. I know exactly what I'm looking for, so even though they look tiny, if I don't find them here, I know the second place to look for them. That's the stuff we looked at last time. All kinds of stuff. No, I don't know. So let me go somewhere else. This is the other alternative. Have any of you found any photos on here? I thought there was a whole, oh, maybe I took them off. I thought I had on this website a whole bunch of photographs. Overview syllabus. Perhaps I took them off. So I see one down here. Actually, they're in this little. Okay, so I'm going to use this. So the idea is very straightforward. This is what I was looking for particularly. And so you need some kind of seismic impulse into the ground. And then you lay out some geophones which will measure the first arrivals. So the geophones are typically just a magnet with a coil on a weight that hangs inside it. If you take the casing of the geophone and shake it, then the magnet is attached to the geophone so it moves. The coil is just suspended in there. And so as the magnet moves, the coil has inertia, and so it moves relative to the magnets. If it moves relative to the magnets in a magnetic field, then it creates electrical impulse. And so that electrical impulse is what you measure. So that's what the seismic waves are that you see in a seismogram. So you lay those out along a section of a path, and on that path you provide some shot. So the schematic is this. So you have a geophone that you put out at a variety of locations along a traverse. Which would just look like this, I guess. So you have geophones physically arranged along a traverse. These might contact into a measuring unit, which could be in a vehicle. A measuring unit could also be physically on something that is backpackable. You can't see this very well, but this is a guy with a little portable unit sitting on snow-covered ground in western Alberta, as it turns out. And then all you do is you provide some kind of motive force to this. And this motive force might be hitting a steel plate with a sledgehammer, where the sledgehammer has an electrical contact on it, so that when you hit the steel plate, you make an electrical connection, and it gives you time zero in your recording, and so you can record everything next to that. It could be that it is a shotgun with a shell in it that you shoot at the ground that gives you an impulse by hitting the ground. Or it could be a quarter stick of dynamite that you bury in the ground or put in water and explode. Or it could be a slightly larger, much bigger explosion, depending on the size of the area you're looking at. So in terms of environmental geophysics surveys, the depths that you're looking at might be of the order of 10 or 15 meters. So maybe 10, certainly no more than 100 meters deep. And so the length of your array that you use might be, say, if you have 10 geophones, it might be 10 times the depth that you want. So it might be 100 meters long, or it might be a kilometer long. A kilometer would be large. If you're doing this in the oil patch, exactly the same techniques. If you fly over any parts of the US or Canada for that matter, you see these long lines which are cleared forest apparently in the middle of nowhere. Usually those are cut lines which are often have been used for geophysics. So you clear out that area, you run geophones along them. It may stretch for 50 kilometers. and then you provide a shot, and that allows you to look at 5 kilometers deep, which might be the depths of your reservoirs. So that's really all it is. So you provide some shot, you measure the arrival times at each of these locations, you might measure the full waveforms as well, and you put together a picture of those arrival times. And so clearly, if this is the case, if there's a geophone here as well, you can do one shot here, and if you measure the first arrivals versus the location, then the first arrival right at the point where you have the explosion is at 0 time. So this is space in x, this is time. The next geophone you have would measure it later as it goes in 2 modes. So now we're ready to start talking about the different modes. So the waves that travel go in 3 modes. They diffract, which we don't care about, they refract, and they are reflected. So the idea is that once this wave goes down from this source, it'll hit this interface. It has 2 options if we just ignore diffraction. One is that it can choose to go along this interface and travel here, which it will do, of course. And it can choose also to reflect up and back to the surface. It'll do all of those things. It'll refract, diffract, and reflect. And so what we can do is, if we measure these things at the surface, we can measure the first arrivals. And sometimes those first arrivals will be the reflected wave because it comes down here and bounces back. But if this velocity here is large, much larger than this one, you can imagine that a wave traveling down here could travel along here and then refract back up to the surface and arrive at this point faster than the wave that came down in this slow material and traveled all of the time in the slow material. So at some stage, if this is a high velocity, it's going to be faster to go down, take the interstate, travel along the interstate, and then back on the slow roads, then go all the way on the slow roads. As a metaphor, I guess, for that. And so, at some case, the events that go through here and refract and then travel back up to the surface will arrive back faster than the ones that are reflected. So this is the idea here. This is, again, the distance from the shot. This is the travel time it takes. If you're looking at the reflected wave, as you look at the first one would be this one that comes back up to this point here, and that would be this amount. If you look at the one that goes a bit further along and did this, then that would be this one here. So there's a whole series of these points that would be the reflected wave. If you go twice the distance along here, the travel time will be twice as long in going through here, and therefore it has this single slope to it. But if you look at the refracted wave, for the refracted wave to do this, it's got to go here, along here. No, it's got, yeah. So the refracted wave, until it gets to this critical point where it's the same amount of time to do this, this, and this, as it is to do this and this. That's this point here. And then after this point, it's going to be faster to go into this lower, faster material and to go all the way across here, which would be this. And so what you'd expect to see if you look at the traces for these geophones for the first arrivals, in other words, the first impulse you feel, it's going to be the reflected wave for the first part, and then for the latter ones, it's always going to be beat out by the refracted wave because it's spending its time going through this second one. And so if you look at this figure over here, that's kind of exactly what you see. You see the first sequences of these geophones are measuring something that looks like this. And the ones after that are measuring something that is on a different slope. And so this is the same graph. This is travel time versus distance. Travel time from the shot point versus, travel time from the shot point versus distance. And so when you look at the refracted system, what you get out of it are 2 pieces of information. You get the time where this arrival switches over from one to the other. And you also get the slopes of these two lines. So those are the two basic pieces of information. And so you get a slope for this. And so this slope here for the reflected wave is merely some indication of the travel time multiplied by the distance traveled. And so this gives you, the slope of this is just the seismic velocity. In this case, if you do a height of 1 and the length of whatever it is, the seismic wave of material 2 and of material 1, this is 1 in each case. So the acoustic velocity in this lower material that it's going through is larger because this line here is larger than it is here. And so the two pieces of information are you get a magnitude of the velocities of the two layers from these slopes of these curves, which is this and this here. And the other piece of information you get is this critical travel time, T sub c. And using this in some way gives you the ability to be able to figure out exactly what this depth is. So those are the two pieces of information. And so in seismic refraction, which is the most used one, I guess, in environmental applications, you interpret this in terms of those two things. The seismic velocities from the slopes of these and the distance of the layers from this intercept here. To get the most bang for the buck after you spent all the time traipsing across here and laying out these geophones, the other thing you can do is you can do a shot point, which is some other location. So now you take your impetus and you put your quarter stick of dynamite here, and then you measure the arrivals relative to this point, and you get a trace here. You take it to the next point, you shoot it here, and you get another trace. And so what you can use is you can use, again, all of these different pieces of information to get the acoustic velocities of each of these layers and also the critical changeover time, which allows you to basically profile underneath these geophones to figure out what the depth of the material is and what you expect the acoustic velocities are to be in these things. And so if you happen to have a borehole that exists here that you know has in it some length of one material followed by some length of another material, then this allows you to map with some confidence between them, just from using geophysics. So geophysics used to be and is still commonly used in environmental site investigations. It used to be that seismic reflection used to be the domain only of the petroleum companies. And the reason for that was that if you're using it in the mode for looking at relatively short travel times, was that if you're working at maybe only a depth of 10 meters, the travel time to go down to this layer and come back is so fast that it's tough to be able to discriminate between the first arrivals. And so typically it wasn't used there. But I think the equipment now is good enough that seismic reflection is also used in very shallow investigations again. The idea with seismic reflection, I guess we got some pictures, is very, very similar to seismic refraction. But now it starts to look much more like the profiles that we had for instance, Gpr. So you have a source. It might be a shot point with dynamite, or it might be some continuous source. Sometimes vibro size. You see these trucks. I was driving in Alberta, I think in November, and there were 3 of these trucks just sitting by the roadside going somewhere. It's just like a grader that you see for grading roads with this blade in the middle, blade taken out, and instead there's this big weight. A pad goes on the ground, and you presumably have a reciprocating weight that's driven by an engine that drives some frequency and puts this low frequency signal into the ground. And you use that as your excitation. It puts in some kind of harmonic excitation, and again you're measuring the travel time between initiation to recovering it at the surface and a geophone. It's really not very different from the transmission and receiver idea for GPR, often plotted as a trace. If you look at these signals of this would be location in the x direction for your geophones. This would be time of the first of the signal in the vertical direction. So initially at this geophone, for instance here, at time 0 there's no signal. You wait a little bit of time until the first arrival arrives, and then there's a negative arrival, and it just keeps on popping. These are just these individual waves being colored differently for the compressional arrival versus the tensional arrival. So that's what this darkness is. And so what you can then use is you can use this slope as basically an indicator of the first arrivals. And if you can correct that for the length along the traverse of what this individual distance is, you can make this now into a feature which accounts for basically the idea that these would represent stratigraphic boundaries. And so I suppose what you need to do, this first arrival represents when the reflection comes back to here. So if you took this first arrival and dragged it up to the surface and plotted it here and dragged the rest of the trace up with it as well, then what would come out of it would you'd end up with a corrected trace that would actually give you the travel time since the first arrival versus the location along this trace. And that's exactly what this lower figure is. And so these would be the travel times. This is time going down here. This is location along the horizontal section on the surface. And these individual first arrivals would be indicators of different interfaces that have different acoustic impedances. So it'd have a different product of velocity and density, which would be the reason why you get actually a signal reflecting from it. But the travel time between the surface and the feature, or the two-way travel time between the surface and the feature, would be what would turn up in this. And now if you know the velocities of these components, you can convert a travel time. This would be in milliseconds, I think, for these. Yeah, is in milliseconds, I guess. You can use this two-way travel time to figure out what this depth is. And so this actually even looks like the trace. You just have to correct it for the depths that you have here. So these would be these features that are picked up in this particular trace here. Okay? And lots of techniques you can use. So that's basically, so it used to be the domain of the oil companies, but now not vibro-size, but regular seismic reflection work is done not routinely, but quite inexpensively. The most basic of equipment are a piece of equipment called Bison. Don't know why it's called Bison, that's the name of the company. But basically is some geophones that you put out, a box which is the size of a car battery which records the first arrivals and processes it, and a sledgehammer that has a cable on it and a connector. You hit a steel plate, you complete a circuit, it knows the time of the first arrival, it measures the pulses as it arrives in maybe 10 geophones, it corrects them by pushing them all up to the 0 line here, and this trace then is one that you can use to be able to figure out what the stratigraphy is. So geomagnetic methods, geoelectric methods, AC, DC, electromagnetic, seismic, use the velocity as the proxy. Gravity methods is the last one, which use changes in the gravitational field. And so, as you know, if you stand on something which is very dense, has high density, like an ore deposit, the local gravity there is increased by that feature. Because gravitational attraction between bodies are controlled by their mass. And so if you look at, so you can use gravity methods to basically discriminate places where you have lower density materials. And so the ultimate lower density material might be a cave in karst, where you have air in the subsurface versus the material around it. And so the gravitational attraction to a weight in an instrument to a pocket of air versus to a pocket of rock is different. And so if you have something on a spring, it'll be more heavily pulled to something that's rock than it is to something that's air. And so basically gravity methods measure the change in the G constant, which we always assume is equal to 9.81 meters per second squared, but the reality is it varies by some small amount, some very small amount. And if you can measure this very small amount by having an instrument that has a weight hanging in it, and you measure the force that that weight is pulled to the ground with, you can calculate what the change in this gravitational attraction is. And if you know what that is, you can infer what the missing density is that you have somewhere in the subsurface. And so, not so useful in environmental, but it is if you're looking for caves in karst, which might be fantastic conductors for contaminant plumes. It could be useful if you're looking for tunnels under the DMZ in Korea, which is what it's used for as well, to be able to pick out tunnels to see if people are trying to burrow under into South Korea from north, or the other, vice versa. It just uses Newton's law of gravitation to look at the distance in the pull between two objects of two different masses, the Earth versus other components on it. And I guess this is the kicker here, right? It's trying to measure changes in this gravitational constant, which is 9.81 meters a second squared, to a millionth of that, right? 10 to the minus 5 of this is 10 to the minus 5 meters per second squared is a millionth of this. So it's just trying to resolve those magnitudes. So it does that. A typical instrument is like a theodolite that you see surveyors working with, put on the ground, the size of my head, your head for that matter, put on the ground. It's has a tribrac on the bottom that allows you to level it. Thank you. And once it's level, you can measure gravitational things. The problem with it is that this very small signal that you get, that you're measuring, is a function of a whole bunch of different things. It depends where you are on the surface of the Earth, poles versus equator. It depends whether you're at 5,000 feet standing on top of a mountain versus in the Nittany Valley at 1,000 feet. It depends on the topography around you as to whether you have, if you're standing on top of a mountain, that all of a sudden you have this area here. If you're taking your measurement here, all this is air, versus if you're standing on a flat feature where this is actually solid. It depends on earth tides, because earth tides are measurements, or fluid tides for that matter, are measurements of what the effect of the moon is on the Earth. And so the presence of the moon has an effect on the local magnitude of gravity as it goes around. And then finally, the thing that you want to know is what the density variations are on the subsurface. So the problem is that these other features actually might be much larger than the excursion that you're measuring due to your missing soil that's present in the subsurface. But it is used for some, I'd say, exotic things, like looking for karst limestone, which is an important thing here. So those are the four main categories of geophysics, surface-based geophysics. And so we've talked about the fact that for each of them, what we'd like to do is apply it relative to some control. The control is you've drilled a hole in the ground, you do this geophysics, you make some interpretation of it, and you try and make sure that the interpretation is congruent with your drill hole. Same materials, same distribution with depth. And so that's one way in which to use it. The other way, which is used slightly in the environmental area, and absolutely in the petroleum area, is well logging. We made the point that often when you drill, sometimes if you drill wells by percussion methods, not rotary methods that take cores, not augering methods that also do sampling, but straight tricone drilling methods that don't actually take a sample, then you physically don't really have much idea of what's down there. Maybe you get the chips that come up in the drilling mud that you can look at to see what the different materials might be. And also you could put a borehole camera down there to see what the rocks look like after the fact. and maybe look for fractures, which you can certainly do. But of course, a borehole camera is just an optical way of doing other borehole geophysics. It's a signal that you're using as a proxy. You see the fracture, you see the rock, it's a proxy to understand exactly what it is and classify it. You're using its texture or the fact that you have these planes in it to say something about it. So you can also use other proxies to be able to figure out what's going on. And so that's something that's been developed in the petroleum industry over the past, I don't know how long. Certainly 100, probably not 100-ish years, but certainly 50, 60, 70, certainly since the 40s, I would think. And the idea is to figure out by some proxy what there is in the subsurface. So you have a sonde. A sonde is just an instrument that's a tool that's physically hung on a wire line, and it's dropped down the hole. It's dropped down the hole at constant velocity. It has to be an uncased hole, so there's no casing that it has to look through. It doesn't go down discretely, but it just is dropped to the bottom of the hole, maybe a meter a second. It's dragged up through the hole, maybe at a similar rate, and it records some signal as it goes down and gives you a constant profile recorded as you go down, both ways. And you can use that to measure a variety of things. And the signals that are used typically are to measure natural gamma radiation. So gamma radiation is put off by decaying components, typically in clays or shales. So the presence of gamma rays is often indicative of clays or shale layers. So they might be aquifers or aquitards, or they might be aquitards or aquicludes for you. So you might want to know where those are. You can use a cesium source and the backscattering to figure out what the density is. And the density might be some indicator also of a material individually. You can use a neutron log, just like you can use a Troxler instrument. If you've ever been involved in any construction work and needed to measure the moisture content of soils that you may be compacting with a tool, then you can take an instrument that has a neutron source in it. It measures the backscattering off the hydrogen atoms to figure out how much hydrogen is in there. Hydrogen is water, and it gives you a reading, a calibrated reading of moisture content. So a neutron log can also be used downhole. It can be used to measure the electrical resistivity of the wall rocks that it goes through to be able to correlate with your electrical resistivity survey from the surface. It can measure the electrical resistivity of the fluids and correlate that, or usually correlate that with this, whether it's got salts in them. Measure temperature of the fluids. Can measure the acoustic velocities to be able to use in correlating against seismic data, either reflection or refraction. It can measure caliper, the opening of the borehole, whether it's broken open. Typically that's a measure of some of the, whether it's competent rock or whether it's soils, which you might want to know. It can measure flow rates. A Spinor Log is something that just has a tiny little impeller on it, like a torpedo. Instead of a torpedo being driven by the impeller at the back, moving at some fast rate, here the torpedo is the sonde that's dropped down the borehole. As it goes down, it pushes through the fluid, and the impeller is activated. You run it down the borehole, measuring the velocity of that impeller as it goes down. You pull it back up, you measure the velocity as it comes up, and if you subtract the two velocities, you have some idea of the static flow in the hole. How much water is coming in at section A, flowing up the hole, and then flowing out at section B allows you to get an appreciation of what the hydrogeology is by looking at that. And the deviation is to see how off vertical it is, if you wanted to know if that's important to you. And so typically you'd measure each of these signals. So depending on what you want to figure out, you could measure gamma rays if you're looking for aquicludes. You might measure acoustic measurements because clays would have lower seismic velocities than sandstones, for instance. But usually the interpretation of these relies on having a bunch of these signals that together, when you look at them in the ensemble, you can make discriminations as to what the lithology is as you go in depth. And that's basically what's done. So you run a density log and look at density changes. You look at gamma ray counts. High gamma rays would be shales. Low gamma rays would be not shales. You measure conductivities and self-potentials. And then once you put those together, you come up with some interpretation of what the materials are as you go down the hole. And so you use that as a proxy, maybe for taking core and being able to look at the core to be able to understand what's going on. So the different instruments, they all kind of look the same. Sometimes they'd have a bow in them to be able to press them against the borehole wall. Sometimes they would have a little lever that does the same thing. Sometimes they'd want to be put in contact with the borehole wall to be able to get this radioactive source to measure back scattering in close contact with the wall. Sometimes they might be measuring how open the borehole is, like a caliper log with a little lever here. And sometimes they would use coupling with the fluids in the hole to measure acoustic velocity. So acoustic velocity in a hole, you have a little pinger source that kicks out a seismic pulse. The seismic pulse goes through the fluid to the wall, goes along the wall, comes back off the wall through the fluid, and is measured in the receiver, actually in the sonde. And it measures the travel time, time of flight, and it uses that in exactly the same way to be able to figure out what's going on. So these are used sometimes in environmental holes. They're used almost always. They're used almost every time you drill a hole in a petroleum hydrocarbon hole. And then they're used to interpret what's going on. They run quickly. Some of them have radioactive sources in it. If you stick it in the hole, you're basically required to pull it out of the hole to not leave a radioactive source in it. I'm not sure how that happens if it gets stuck in a really deep hole where you physically can't get it out, but that's the deal. And so together, we've talked about a whole bunch of different methods of measuring these things. And so I won't belabor the point as to how they might be used. We've tried to really focus on the ones that are kind of important. And so the ones that are typically used are electrical methods, Gpr is used, seismics are sometimes used, and some other borehole methods are used less frequently. But at the end of this little section, there's a useful component that talks about these different methods. We can go back to the previous one, but this is perhaps a bit more graphical in terms of what it does, is it looks at the different uses of these things. So seismic methods are the ones we talked about in terms of surface seismic, refraction or reflection. Seismic monitoring might be, for instance, if you have a CO2 repository and you want to monitor how saturations of CO2 are changing at 3 kilometers depth, then maybe you do a seismic survey once, measure the profiles of the velocities. You put stuff in there for 2 years, and then you measure the seismic velocities after 2 years, and you should be able to pick up locations where it's saturated with a gas versus saturated with a liquid, because they have different acoustic velocities. Sonar for lake surveys, gravity methods, magnetic surveys, resistivity methods we've talked about. Electromagnetic methods are the big picture ones that we talked about. Gpr, we said, is quite useful. Resistivity, we said, is quite useful. And time domain reflectometry we spent no times on. And borehole logging we've just talked about. So the kinds of things that you might want to be able to use them to figure out. Where does soil go into rock? Yeah, seismic for sure. Radar for sure. Resistivity methods, yeah, probably, but the signal between soil, resistivity contrast isn't large. And so picking up features like faults, certainly seismic would work well. I don't know why magnetic would. Fractures, buried channels, etc. So in other words, contrast in these different materials. And so if you ever find a need to be able to use any of these, you can choose them based on their different applicability. Buried drums we talked about in terms of magnetics. Obviously you're picking up a ferric target, you should pick them up, etc. There's a different one here that has some different ones, mainly the environmental one. This comes out of Cohen and Mercer. ground penetrating radar, other electromagnetics, resistivity surveys, seismic surveys, MD, I don't know, does it, magnetic detector is people hunting around on beaches for coins, is a metal detector, a magnetometer, and organic vapor analysis. So in other words, sticking a capillary tube into the ground, sucking on it using basically a gas chromatograph to be able to figure out whether organic vapors are there, and the expected source of them being VOCs, I guess. And so you can think about the different applications that you might want to use these as well. And so they can be used in a variety of different applications, so depending on the need. But the basic ones are GPR is used widely, resistivity is used widely, seismics are used somewhat, can't pick up plumes, for instance, and magnetic methods are very straightforward, but are not very useful unless you're looking for buried trunks. And so those are the various methods that are used. And so the idea is boreholes, very limited, very accurate, because you know what you see is what you get. And therefore you're quite sure about what's there, but they are only a speck in your whole site. And to be able to fill in between those different locations, what you can use is some form of geophysics. It comes in a variety of different packages, all using a proxy for some feature of different rock types to be able to identify those different rock types or the plume. And so they have some measure of uncertainty attached to them, but if they're benchmarked against some direct investigation, then you have some reasonable confidence in what's going on.